sequences now. Oh. What Dr. Seuss book are we talking about? Yeah. One fish, two fish, red fish, blue fish. I thought it was cute. I've probably seen it before. All right, just watch, okay? We're trying to find the common ratio, and so you just set up the ratio. And what does that equal? 3/2. Well, if you set up the ratio of the next two terms, it's a little harder to figure out, but this is 4.5 doubled, and this is 4.5 tripled, so it is equal to the same ratio. And with the geometric sequence, that'll always be true. You set up any ratio in any two terms, you get the same thing, same constant ratio. It also means, by the way, if I were to do the first term times that common ratio, well, look, what do I get? -3 there, so 9. If I did 9 times -3/2, I'd get the -13.5 and so forth. So that's how you generate a geometric sequence. Watch this one. So you don't have to write it down. But I'm going to do the same thing. I'm going to set up the ratio. I'm going to do the second term over the first term. Okay? So I want to factor these first. What is the common factor of these two terms? Now, I heard 3, which is correct, and 9, which is correct. 27 is correct, but 81 is the best answer. Because how many times does 81 go into 243? 3 times, because that's the next power, right? And the next one after that, by the way, is 729. So the common factor is 81. Really, you want to factor out negative, because the least coefficient is negative. And, well, I'll just go, you factor out of there, you get that binomial. Here, the common factor is what, Caleb? 243. And you factor that out, you get n minus 3. So now, what do I cancel, Hayden? What else? Good. Or what else? I can't hear you. Yeah, but okay, come on. What goes in 81 that also goes in 243? 81. How many times does 81 go in 243? 3 times. Actually, these are all powers, so it's easy. Divide here, you get -1. Divide here, you get 3. So the ratio is -1/3. Let's do it again. If I do the third term, which is smaller, that's a nice thing, over the second term, I should get the same ratio. Here, the common factor is what? And take 27 out, I get that. Here, 81, -81. That cancels. 27 cancels, leaving -3. Same ratio. Which means, if I were to multiply this by -1/3, I would get this. Multiply that by -1/3, I would get this. So take it next. If I multiply this by -1/3, what is the third of 27? But it's -9 because it's -1/3 actually. And then what? Plus 27 because the third of 81 is 27. That's the next term. What's after that? Positive 3n minus 9. Next one. -1n plus one more. And you can keep going. Okay? All right, I'll let you write this one down. So the ratio of the second over the first looks like that. This is harder because, frankly, they're not just powers. So I'm going to take the easy way out. I'm just going to take half of both times. Half the numerator is that, half the denominator is that. Take half of again. And you could have figured out the common factor. And then divide by 3, you get 7/2. So we could have divided both these by 12. That would have been the fastest way, but don't worry about it. I just find the common factor. Now, let's double check. It's the same thing. It should simplify to do the same thing. Take half of again. 47. Half of 28 is 14. Going into 1. And half 14 is 7. And that's 42. Can't divide by 2 again. You can divide by 3 because 1 plus 4 plus 7 is 12, which is a multiple of 3, so you know that's a multiple of 3. And then you get 3 goes into 14 4 times, and 3 goes into 27 9 times, which means 9 is right. We're dividing by 3. What's 42 divided by 3? And I'm pretty sure that is the same ratio. So here we go. And then we're not going to actually do this, but if you multiply this by 7 halves, you get this. This times 7 halves, you get to this. This times 7 halves, you get the next term, and so forth. All right. On your green note sheet, take out your green note sheet. Write that down for the common ratio. And we're going to do like we did for arithmetic. And in the same box, we're going to write the recursive formula. This is the definition of a geometric sequence. It's one where you have a common ratio that's constant. If you rewrite that, you get this. So, which says if you multiply the previous term by r, you get the next term. Actually, I still have that here. Go ahead and put. Okay, this is your nth term formulas for the next box where it says an equals. Write this. That's called your explicit formula. And at the bottom of the screen, you see I have the recursive formula again. Stated a little differently. I mean, it's the same thing. It's just times r afterwards. This part here is optional in terms of writing down. Just realize that you don't use the recursive formula to find the first term. You usually find everything after the first term. Okay? Actually, remind me. I should show you the Fibonacci sequence. Okay, we'll do that next before we get into. I don't know. I'll show you. It's not a geometric sequence, but somehow it didn't get in there when we introduced sequences. So, and by the way, one more thing. If you look at the explicit formula up here, once again, the same idea as the arithmetic. And what I mean is, here you're multiplying repeatedly, and multiplying repeatedly is doing a power. That's why it's a power. And you get from the first term to the nth term, you're going to multiply by r n minus 1 times, which is why the formula looks like this. Now, here just write this down real quick. The Fibonacci sequence. Doesn't fit here, but I don't know. It is. Exactly. These numbers come up in like spirals in a pine cone, sunflower. That flowering plants, like as the leaves rotate around the stem, the number of leaves it takes before it repeats, like completes the revolution on the stem, is usually almost always a Fibonacci number. So yeah. Anyway, so here's the recursive formula. Sorry, I was thinking like computer science. Start with the first term. So the first term is 1, second term is 1, and then the nth term is found by adding the previous 2 terms. So if I was going to list the qualifier here, the recursive rule actually only applies to everything after, for the third term and after. And so that's always going to be the case where the recursive formula is expressed in terms of the previous 2 terms, then you need to be given 2 terms to start with. Okay? And so if I want to write out the sequence, I start with 1, followed by 1, because it said so, followed by what? Because the previous 2 terms add up to 2, and this thing just, there it goes. And then 1 plus 2 is 3. Then 21, 34, 55, and on and on and on, 89, and it goes on forever. And that's the Fibonacci sequence, which is important because it comes from nature. The book actually talks about the golden rectangle, the golden ratio. And I'll just show you real quick. Since we have these numbers here already, if you do 1 over 1, and then 2 over 1, and then 3 over 2, and then 5 over 3, and then 8 over 5, and then 13 over 8, and then 21 over 13, you take this limit, which is just numbers from the Fibonacci sequence, then that approaches what's called the golden ratio. which you can look into if you like. But it's a special number. Anyway, moving on. Back to geometric sequences. Write this down. So, while people are writing that down, here's the formula once again. The explicit formula. What is R? No, but I mean this for this problem. -2. You're multiplying by -2 repeatedly. Yes? So, negative what? No. You're multiplying by -2. Yeah. I mean, think about it. If you try to add, you add 3 here, but then you subtract 6, then you add, you're not adding a constant. It's not arithmetic. Yeah. Now listen, there's our explicit formula. Once again, it's just the first term times r to the power of n minus 1. I want to use this explicit formula to be written 2 ways. Okay? And so, it'd be nice if the exponent wasn't n minus 1. So, here's what we're going to do. If I were to multiply this power form by this power form, write that down. Basically, I didn't have n factors of the -2. I had n minus 1, so I need one more, so I multiplied by one more. I had these exponents, so don't I get an n for the exponent now? So I'm going to do that. The problem is I can't do that without changing the problem. So I need to counteract that. In other words, if I multiply by -2, but then also multiply by -1/2, doesn't it equal 1? So I multiply this part of the problem by -2 to make this nicer the way I wanted it. And over here in the front, I'm going to multiply by the -1/2 to counteract that. Thereby getting another version of the formula that has an exponent that's just a little bit nicer. So I'm asking you to give me both the original that this gives you, and then a version where the exponents just end. So that's your explicit formula, written 2 different ways. Now the recursive formula, which is really easy. You start with not R, but the first term being -1. And then how do you get the following terms? You keep multiplying by -2, right? So you say, okay, -2 times the previous term is how I compute the next term. So -1 times -2 is 2, 2 times -2 is -4, -4 times -2 is 8, and then times -2 gives you that, times -2 gives you that, and you can just keep going forever, right? So that's what this describes, is that procedure. And of course, don't forget you have to write down how you started. Otherwise, it's an incomplete definition. Okay. Yeah, we'll do this one. Sorry, was everybody ready? All right. Just write down the new sequence, same directions. Just write down the new sequence for this example. R is a little more challenging. It's not horrible, though, actually. Because, look, I mean, if you multiply 3 by 5, you get 15, which is too small. 3 times 6 is 18, which is too big. So I'm guessing 5.5. What's 3 times 5.5? 16.5. So, and presumably, they're right, it's geometric, so that 16.5 times that would give you the next term. I'm not going to check it, frankly. So, our nth term formula is, well, what, Thomas? 3 times r, which is 5.5 to the power of. There you go. But I want to put it in 2 forms again. So I'm going to multiply this by one more factor of 5.5, which means I need to counteract that over here by dividing by 5.5. This now has a nicer exponent, like I was trying to achieve, and this is just ugly. I'm going to leave it ugly, frankly, because there's not much you can do with that. So it's not wonderful, but at least the exponent's nicer. The recursive formula. Madison? far right for the recursive formula. A1, yeah. What's the first term? Oh, you're going to, I'm sorry. Well, first of all, write down the first term, and then an equals. As far as 5.5, then what are we doing to get from term to term? In other words, what do you do with the 5.5 and the 3 to get the next term? Multiply or add. Multiply is 3 times 5.5 is this. 16.5 times 5.5 is this. And then times 5.5 gives you the next term, times 5.5. So I'm saying it's always 5.5 times the previous term that gets you the next term. And it's always going to look like that for geometric. With arithmetic, I was adding on the common difference, right? And by the way, I do need to say, not everything's arithmetic and geometric. That's going to be our focus. But I just showed you one that is neither. You start setting up these ratios, they're not all the same. I mean, definitely not all the same. They tend towards something, but they don't equal each other. Is there a common difference? No. That's the difference of 0, the difference of 1, difference of 1, difference of... Oh, yeah, I forget about that. The differences are the Fibonacci sequence. But anyway, not arithmetic, not a common difference. So I'm just saying, not everything's arithmetic and geometric. We're going to move on. Try this one. And I'm sorry, was there a question? No. Quadratic, like you do, the difference of the difference, you'll get a constant if it's quadratic. Cubic, third time out, you get a constant. But that's just another possibility. There's a lot of different kinds of sequences out there. Now, sorry? Oh, yeah. Listen, if you wanted to major in mathematics and then go and get your master's in mathematics, there are literally thousands of specialties that you can do research in. And so it's a huge field. And there's so much I don't know. Yeah. And when you get into real mathematics, it's story and exciting. This stuff was all discovered at one point, and you get it handed to you, so you don't appreciate the centuries it took to figure this stuff out. Seriously, the Greeks had trouble multiplying because of their methods. Okay, and then they had trouble with algebra until they developed a better system that you get to use. So I mean, just learning how to write math took forever. And then things blew up once they started getting better tools. So, all right. Anyway, what is R? And once again, if you can't just tell by looking at what R is, then divide two terms. And if you do the 2 divided by the 3, you get 2/3. Okay? Just for the record, just watch for a second. Just to show that this really does work. If I do the first term times 2/3, that does equal 2, doesn't it? Then if I do 2 times 2/3, that's 4/3, isn't it? And then 4/3 times 2/3. Well, times 2 gets you 8, times 3 gets you 9. What's the next term in the sequence? 16 over 27. Next term. 81. It just ends up being powers of 2 over powers of 3, doesn't it? So, now back to this. We're supposed to find the ninth term. We're going to do it using the formula. So let's write an nth term formula first. The first term is 3. R is 2/3, we said. Let's probably put that back over here. To the power of n minus 1. So there's the formula we're going to use. We're trying to find the ninth term. A is with my 9s, but that is a sub 9. N times 3, it's 3 times 2 to the power 2/3, the power of 8. Right? Now, look. This ends up being 3 over 1 times 2 to the power of 8 over 3 to the power of 8. Now realize that this 3 is going to cancel one of these, so you're really dealing with 3 to the power of 7. You want to cancel first before you start cranking things out. 2 to the power of 8 you should know. 256 is correct. Be careful, people are quite often off by 1. Someone said 512 with another period, 128, no, it's 256. 3 to the power of 7, 2187, we did it earlier. You're supposed to know, though, 3 to the power of 6 is 729. If you knew that, just multiply by 3 and get 2187. There you go, we're done. Listen, this one, once we saw the pattern, it wouldn't have been too hard to extend the sequence out that far. But the expectation is that you're using these formulas. Okay? So on the test, plan on using these formulas the vast majority of the time. Alright, now the recursive formula for this is really easy. What do I put first, Hayden? And then how do you find each term from the previous term? Yeah. Okay. And that's what we were doing, by the way, when we got to 16 over 27, 32 over 81, and so forth. It was basically using the recursive formula. All right. Something a little different. No, not that one. Just watch this one. All right, so you have an initial value of 225,000, and then the value appreciates by 3%. But I want a formula that gives me the value of the home after so many years. So my question is, what are you multiplying by to get the new value of the home? Not 3. Not 3%, but 103%. I mean, it's increasing by 3%. But I mean, if you multiply by 0.03, you get a decreasing sequence. That is wrong. So in other words, here, watch. The formula that generates this sequence is 225,000 for the initial value times 1.03 to the power of n minus 1 because it's growing at 3%. So you multiply by 1.03 to get the new value, and there you go. Moving on. Now look at this. I told you before why arithmetic sequences are called arithmetic. Geometric for the same reason, more or less. It's because, here, any term is the geometric mean of the term before and after it. Which means I should probably explain what a geometric mean means. You simply take the product and take that root. So for 2 numbers, you take the square root of the product. 3 numbers, you take the cube root of the product. 4 numbers, you take the fourth root of the product. That's how you find the geometric mean. So we're just doing 2 numbers, so it's easy. Do the number 4 number after, you get 36. Square root of that is 6. Then for the 12, the numbers before and after have a product of 144. And the second root of 144 is 12, and that's how a geometric sequence will always work. Every term is the geometric mean of the term before and after. By the way, as far as uses of geometric mean, here's just one. If you had an area, and you want to find a square with the same area, I mean you have a rectangle, you want to find a square with the same area, the side length of that square will actually be the geometric mean of those side lengths. So you can find that side length directly. There's other applications of geometric mean. Frankly, there are some cultures that think that way. You ask them, the average, and they average in terms of ratios. Whereas you ask us the average, we say, oh, well, add up and divide by 2, or and so it's a different way of averaging, different way of thinking, really. But it has certain applications. I need to find more. I forget the other ones. All right, write this down. And someone has a calculator, take out a calculator. Because frankly, the numbers here are a little bit unwieldy, to say the least. So I didn't notice until I started this morning, and I'm not going to change the example. So, but write it down. And the procedure we're going to do is exactly what you would do on the test without a calculator, except for the numbers would be nicer. So it says there's just 3 terms between these, which means this last term is the 5th term, yes? So how many times do you have to multiply by r to get there? 4 times, right? So you might even write that out. Times r here, times r again, times r 4 times. So what I'm saying is, if I did the ratio of these terms, that will not be r. That will actually be r to the power of 4. So someone with a calculator now, figure out r. Take the 4th root of that. Tell me what you get. It really is 0.25 when you round it. So it turns out to be a 4th. And go to, I'm going to let you do this first too. What is the 4th of 264? And then divide by 4 again. And if you divide by 4 again, if you divide by 4 again, you get this, and so there you go. That's the sequence we're looking at. Numbers would be nicer for the test, but the same procedure will always work. You know, r to the power of whatever equals that ratio, and take the whatever root you need to take, and you'll have your answer. Well, you have r. All right, we're not doing that one. Write this down on your green sheet where it says SN. Write that down. We're only going to do one version of it. And frankly, we will have one more formula, normally called S infinity, as in the last box, which we'll see on Monday. You sum up a whole infinite series, and that formula is much nicer than this one. That's the good news. This is the worst of it, this formula here. Correct. So, yeah, exactly. Because this was doing more work, technically, because it's adding up the whole infinite series. It just works out much more nicely. And if you think about the example I gave you, when we're doing a half plus a fourth plus an eighth plus a 16th, like that, if the numbers I just said, you get 15/16ths, which is kind of not as nice. But if you add the whole thing, you got 1. And that's how it's going to work typically. All right, here. There's your formula. Here, start writing this first example. If you didn't finish writing the formula, I'm going to put it here anyway. By the way, I messed up my formula. Last period I did it on accident. This period I did it on purpose. What's wrong with what I wrote down? Yeah. Now, first of all, look, they call it A1. You can call it A1 if you want, but that's not a problem. That's just an option. If you can put it out by itself like they did, or you can put it up as part of the numerator. My mistake was to call this thing AN, but it's a sum formula. The formula itself is sound. Like I said, you want to call it A1, call it A1. If you just put A, we mean the first term. Okay? But if you like, there. All right. What is R on this problem in the sequence series? This is a sequence right now. 3/2, right? Negative 3/2. Because you, just for the record, if you do negative 6 over 4, you get that. And if you do 9 over negative 6, it also works out to negative 3/2. So that's R. All right. Oh, I'm sorry. I forgot. We're going to change this to, say, 7. Be happy. 11's just a bit out there. 7's not bad. All right. So let's do our formula. Find the sum of the 7 terms. The first term is the 4. And then it's 1 minus R, which R is this fraction, negative 3/2, parentheses, to the power of 7. All over 1 minus R again, which is not 1 minus 3/2, is 1 minus negative 3/2. I emphasize that because people quite often, if you're subtracting negative, they only put one negative side, and then they're wrong. And then we have to deal with that without a calculator. So put the calculator's away. Yes, this problem could be in the test. All right, let's go through this. Let's do this first. Raising both these to the power 7. First of all, 2 to the power 7 is what? 2 to the power 7. 128. You know, if you didn't know, then do your powers of 2 and figure it out. 3 to the power 7 is 2187. Of course, technically it's a negative 2187 because it's negative 3 to the power. And we'll get back to that. Let me go and clean this up a little bit. And by the way, I meant to mention that right at the beginning, you could not like cancel these signs right now because we had to raise this to a power first, yes? And because it was an odd power, it does end up canceling, becoming a plus and positive, but you couldn't do that here. And if you did, I'd take out points for not knowing your math. Do the power first and then cancel if you can. Here, of course, you can just change that into a plus to positive, and this is 2 halves, so the denominator becomes 5 halves. Right? Now, when you combine these, this does become plus, it's not positive. If I want to combine them, I need to write this as a fraction. This is 128 over 128, isn't it? So I need to add these. All right, just bear with me. So 8 plus 7 is 15, so I'll put a 5 here, the 1. Then the 2 and the 8 is 10, plus 1 is 11, so I'll put another 1, carry a 1 again. The hundreds place is 1 and 1 is 2, plus the 1 I carried is 3, and then it's just the 2. So I'm just saying, those numbers add up to 2,315. The denominator is 128. Now what I really want to do is, so this became that fraction. The 4 that's in front, I'm going to write as a fraction. And the denominator, I'm going to move up to the numerator, dividing by that fraction, same as multiplying by reciprocal. Reciprocal. Say that 5 times fast. And it's just best to string your fractions together like that. And now we cancel. Once again, if you start multiplying these first, shame on you. You're taking a hard problem and making it harder. First here, half of 128 is what? And then if you don't want to divide by 4, fine. Take half of. You get 32. Then take half of again, you get 16. So we're done with that part. Now we have to divide by 5. And you can go over to the side and do 2315 divided by 5, long division, but just bear with me here. How many times does 5 go into 23? So put a 4 there. And then the remainder is 3, which I'm going to put here, which makes that 31. 5 goes in 31 how many times? Remainder. And then 5 goes in 15 3 times, and there's your answer. Over 16. And like I said, if you want to go over here and do 2315 divided by 5, that's fine. You'll get 463. But all the work you showed here is what we did. We did the exact same thing, but all we did was write down a little bit of it. So if you can do that, you save time. So. And we're done. Correct. If you started summing up these terms, that's what you would get. Just for the record, what is the next term in the sequence? Is it a negative 27 over 2? I mean, multiply 9 times 3 halves, and just basically 9 times 3 is 27. 3, that's the numerator. So I'm just saying, it may surprise you to get a fraction because we didn't see any fractions, but they were going to be fractions immediately after. And so it's not really surprising. All right, we will stop there.